So, welcome back, everybody. Just as a reminder, we're talking about relative velocities, and the picture on the board doesn't really have any contextual meaning. It's just saying, look, we can add these angles and vectors together. Okay, as we go through, this is going to give us everything that we need. This resultant that we draw when we go 130 degrees and then 70 degrees, the resultant is what we're after in the end. Now, as we go through here, some problems are going to present themselves a little bit easier. Just so that we have a nice little kind of formula to use, we're going to work through that problem with this stuff in mind, remembering that we can get x's and y's using the magnitude of velocity or its speed, and then just times the cosine or the sine of an angle. So let's kick back over to this problem that's super wonky that we set up and see if we can't use these things to make sense of it. Okay, this is what I'm going to keep referring to over and over for a few minutes, just so you guys are aware. Cool. All right. So we had this problem that I asked you guys to identify the knowns and all of that good stuff yesterday, and here it is. So, Bea, if you should, if you read this problem, you're going to feel like you're going crazy because it doesn't make any sense. Change the word ball to tray, and it kind of works, but I will never give you a problem that's so unclear again. Okay, back at this then. We are given a few things. Real quickly, these look different than anything that we've written this year. What is this? VAT? Good. This is the velocity of the ant in this context, A, relative to the tray, T. Now, we talk about these things and we label them really clearly because if we don't, we're going to get lost. Like, it's going to happen. Now, we can draw and tie all of this stuff together. If we're looking for the end velocity, right off the bat, do you guys agree that the end velocity is some combination of the two different things that we're looking at? Like the velocity, we have to deal with the tray moving relative to the ground and the ant moving relative to the tray, and we have to combine them somehow. And turns out it's pretty easy if we stick to these rules and just this trig stuff that we've started looking at. So here we go. If I'm looking, this one's a unique example. Does the tray have a horizontal velocity relative to the ground? Now, in this situation, all of its velocity is horizontal. But we're going to pretend as though, even if this had been angled, we'll see how this works. So let's jump in, and I'm running out of colors to use. We'll switch to yellow, I guess, for everything that we're going to do. And let's dig into it. Okay, if I want to find the velocity in the end, in the x direction, all that we have to do, no matter how many relative velocities I've been given, we just have to find the x components for all of them and add them together, just like we did with regular old vector stuff. So, as we do this, my notation looks a skosh different than the book, but if you hate it, we can do a different one, and I'm totally good with that. So, I want to know the ending velocity in the x direction once we combine everything. Now, if you wanted it to be more clear, I think that it'd be great to say the velocity in the x direction of the ant relative to the ground, but I think that it starts to look a little bit harder and harder to deal with. If I know that I'm just looking and I'm talking about the ant and there's not more going on, I'm just going to call it Vx. Don't want to muddle it any more than needed. Okay, so let's check it out. How many relative velocities were we given? 2, right? There's the ant and tray and ground. Cool. So going through this, let's just deal with each of them independently and we'll just add them up. Do you know the magnitude of the ant relative to the tray? The velocity's magnitude, or its speed is just another way to word that. So the trays is 0.15, right? And that's what I said, so you're good with that. Okay, so checking it out. Let's just dig in. I know then, I'm trying to decide on how I want to do this. I'm not going to use super ugly notation, but we'll just use it to make sense. If I were to take the size of the tray, the velocity of the tray relative to the ground, that's like my magnitude, right? In the x direction, do I use cosine or sine for the angle that we're traveling at? Is x cosine or is x sine? It's cosine, right? So check it out. And I'm color coding, I think. Here's the velocity of the tray relative to the ground. And if I'm looking for the x, it's going to be the cosine of theta of the tray relative to the ground. They match. I'm just using everything with relative to the ground, that first little relative piece. Now, In practice, I don't expect you guys to do it all the way out every time, but I want to make sense of it. Plus, is there another relative velocity that we're dealing with? The ant relative to the tray, right? So check it out. Here's the x component that we get from the tray relative to the ground, plus the velocity of the ant relative to the tray, times the cosine of some angle that we're told that the ant travels at relative to the tray. It looks super ugly. Maybe. I don't know. Does that look ugly to you guys? A little bit. It's always going to be my suggestion that you actually write out this formula every time. And I know it gets tedious. I get it. I wrote it out every time I did the problems. I'm going to leave that up to you. But on a quiz or a test, remember, always include your equations so that if something goofy happens, I can see where it happens. Cool. Well, before we dig into the why stuff, let's just break this down a little bit and plug in what we know. How fast is the tray moving relative to the ground again? So here's my 0.150, and it's just plugging directly there. What's theta of the tray relative to the ground? $180. I'm good with it. Okay, now there is going to be something strange that happens in here that's a trig issue, but we'll deal with it as we see it. Okay, plus, help me plug and chug here. I'm just going to call on everybody. Kalisha, what's the velocity of the ant relative to the tray? That is loud and confident. I love it. She says 0.050 times the cosine of Huggins. What is the angle theta that the ant travels at relative to the tray? So love that you're giving me one of them, but notice that 180, that's TG, right? That's tray relative to ground. Now we're dealing with ant relative to the tray. So you give me an angle, you just happen to give me the wrong angle that time.
I don't see how it's fitting.
So can you expand on that at all? And that's a hard thing to expand on.
I just don't understand why the ant would be walking at a different angle when it's all flat.
So it is flat, but like imagine you've been to lots of airports and you've ridden on the moving sidewalks, right?
Yes.
Can you imagine a situation where somebody just, like if I'm going this way on the moving sidewalk, here I am, and I walk forward, like I know it's not very wide, but I could walk forward, right? So all we're asking is, if I step forward, what's my velocity relative to the ground? Because it's left and away from that side of the elevator, the sidewalk, right? So with this,
I forgot about the walking west.
Yeah, no, you're good with that. This 180,
Yeah, it's 90.
good, I like the 90. Okay, now this problem, is it cool to use a calculator for? 100%. Now, full disclosure, you don't need it once we do the trig stuff. You can use it, you should use them. But once we do trig stuff, or if you remember the unit circle really well, you don't need trig stuff. Anybody remember the whole unit circle really well? Okay, nobody else though. Cool. I am expecting a couple of different answers, but we'll see how it shakes out. 0.15 cos 180 is negative 0.15. Pretty sure of it. If you get anything other than negative 0.15, negative 0, I'll switch to orange, it means that you are in radians. Please double check whether or not you're in radians or not. Theoretically, no, but cool. Plus, this one's even easier, and I'm going to walk you through. We're just going to start embedding some unit circle stuff, even though it's not our main focus. Here's 0 degrees. At 90 degrees straight up, what's my x value? 0. What's 0.050 times 0? 0. I can do that one in my head as well. If you can't do it in your head, there's no shame in that. That's okay. The unit circle will show up. We have just found that when we combine these two together, and this is a unique example, but we see that, gosh, turns out in the horizontal direction, I'm only going negative 0.150 meters per second. I didn't add or subtract because my ant is walking perpendicular. Cool. Anything crazy happen here? Okay. I want you guys, I'm going to pause the video for a second. I want you to replicate this process, but instead of working in the x component, let's work in the y component. And I'm going to walk around and check here in a second, but at least for this one, in your notes or on this worksheet, I want you to go through the process of writing out this general formula first. It's tedious, I get it, I want it to stick in your head. I'm going to come and look at your papers, so be ready. Okay, as soon as you make the switch, easy, right? The only thing that has to change is the sine or cosine. It just depends on which component we're dealing with. I'm going to skip this line here where it just shows me putting in the exact same numbers and changing it. Here, I just wanted to make sure we're all good with this. Somebody hook it up. We had 0.15 times the sine of 180. That's a 0. Okay, plus 0.050 times the sine of 90 becomes 0.050. Okay, I see that in the y direction then, my ant, relative to the ground is where we're at right now, is walking at 0.050 meters per second. Now, this problem we could have tackled a bit easier, but we're making sure that we can see how this shakes out. Are we done? Like, is this the end of the question? We've completely answered it? What do we have to do? Like, I didn't write it because it gets ugly, but remember, this velocity in the x direction is the velocity of the ant relative to the ground in the x direction. This is the velocity of the ant relative to the ground in the y direction. I'm not asked to find just the components, we need to find the actual vector, right? How on earth do we find how fast it's going if it's going at these two x and y components? Or if we look at this vector that we started with from the beginning, and that was not enough wait time, that was my bad. The resultant is here. We need to find this vector. That's the total vector in the end. How on earth do we find the length or the magnitude of that vector if we know the x and the y? Oh my, Pythagorean theorem. Let's do it. So, I now know that I have the x and the y components, and if you want to add them, we can. This is the velocity of the ant relative to the ground in the x direction, so we'll say vx. And this is where it gets ugly. This is why I don't do it. Like, there's just so much stuff there. This is velocity in the y direction of the ant relative to the ground. I'm okay if we just use vx and vy. I think it's just as clear. Cool. Pythagorean theorem is going to hook it up. I know then that the velocity of the ant relative to the ground is just going to be vx squared. Sorry, this thing squared plus vy squared. That's my Pythagorean theorem. Cool. Using vx and vy that we've already found, solve it. That's me. Weird. Sorry. That was odd. The v is equal to the square root of those, and this becomes a calculator problem. Now, there's one little change that we could have made, but we'll talk about that in a bit. Do I need to actually put the numbers in there for the notes, do you think, or is it clear what I'm plugging in? All right. What do you get, Fern, when you do this thing squared plus this thing squared? Was it 0.16 to start? Or was it exactly 0.02?
That was before squaring, but then after squaring there's an error. Because it's negative.
Ooh, love it. So, there's an issue with the calculator stuff. Somebody who gets an error. What needs to go around, and I will do this. Velocity is equal to the square root of, the x was this, right? Negative 0.150 squared, plus the y was 0.050 squared. If you type this in key for key, your calculator's not going to do the right thing. How come? The parentheses, that whole velocity in the x direction got squared. If you type this in with a calculator, which you all are doing right now, anytime you have a negative, either put parentheses around it, or since we're squaring it, does it really matter that it's negative? I just don't even put the negative in here when I calculate it because it's going to fall out anyway. If you fix these, I'm thinking, unless I was wrong, which it's happened at least once in my life, 0.16. Or if it still winds up with 0.2, it means that we rounded a little sooner here. But I think it's 0.16. Okay, I got one confirmation. I need everybody to confirm for me that we got the same thing. I don't think that's gonna do it. Felicia, your book's not supposed to be in there. Trying to hook you up like this person's 40.
I've got a calculator.
Oh.
It's this one. It's Sean.
Musical calculators. Okay, is this a number we get? Okay, so that's part of it, right? We now have the magnitude, the speed at which we're traveling. The ant, it's not going fast. The sidewalk's not going fast. Turns out, together, the ant's still not going fast. Okay, is that all of velocity, though? Is velocity a vector? So what does it have? It has a magnitude, which I think we just found. We need a direction. Now, for this, if I'm walking, or if I'm moving this way and I start walking, there's an angle that I'm forming at the ground because up and over makes a slant. So when we look at this, if we think back to this diagram that we drew initially, it will be helpful. We're looking for the angle that this thing's traveling at, and I can see there is an angle here. Okay, if I wanted to find an angle on a triangle, how do I do it? Channel your inner Lakota. Ooh, arc something. Could be tangent. It's SOHCAHTOA is what we're really after, right? Now, when we deal with this, there's some strange stuff that just winds up happening with the trig that we're just kind of gonna ignore for now. I know that on this picture, I get these two pieces. If we look at just this new picture that we have, it's gonna be essentially the same, but check it out. In the x direction, if I start, I go negative 0.150. Okay, in the y direction, I go up, apparently, right, at 0.050. And then this is my new one. And it winds up being the same as what we started with just due to the angles that they're traveling at. If I wanted to find this angle theta, what function would I use? What sides do I have? Opposite and adjacent what I've given you right now. In reality, we also know that that's 0.16. Does it really matter what we use? You can use sine as long as you use opposite and hypotenuse. You can use cosine as long as you use adjacent and hypotenuse. You can use tangent. Tangent is the norm. So the way that I'm going to generalize this is if we now need to find our angle, we have our magnitude. I'll star that so I can make sense of it here in a minute. If I'm looking for the angle, I'm going to default to tangent like all the time because I know that I have x and y. The tangent of that angle theta is equal to vy over vx, opposite over adjacent. If I now want to solve, Rafa hooked it up. He said arctangent. Why would arctangent show up? I wrote tangent. I'm going to use a different word. Why would inverse tangent be useful if I've written tangent? Yeah, tangent of an angle finds me the sides. The arctangent undoes this and finds me the angle. So theta is exactly the arctangent of Vy over Vx, which, notice, again, we have them written right here. Ask your calculator to tell you the arctangent of Vy over Vx. Because when we're asked, the question actually asks us to find the velocity of the ant relative to the ground. If I ask you for velocity, it's implicit that I'm asking you for the speed and the direction. Because velocity is a vector, we always give both. And curious to what you guys have found. 18.4? Negative 18.4. Love it. Okay, this we need to make sense of. Negative 18.4. Remember that I erased it and I don't know why. This was a vector that I had for Vx and Vy. Why would we have just gotten a negative 18.4 degrees? Sorry. Why would that make sense? Or how does it make sense? Because does that look like a negative angle to you? Okay, I like that idea. It's because I'm good with that. It's because we're going in negative direction. Couple things that's not too tricky. It feels wrong to me to write negative 18.4 because normally we think of the direction going this, like counterclockwise. However, is it possible that just due to the way we set this up in the quadrants that we're in, that it measures that angle like this instead, and went in the clockwise direction? If we go in the clockwise direction, what's our angle going to be? Like if I say here's 0, right? 45 degrees, and I gotta stand this way. 45 degrees does that, right? Okay, so 45 degrees says start at X and go that way. What's negative 45 do? Just goes the other direction, clockwise. This angle makes sense. We don't have to say 18.4. We can clear this up much clearer, but that's redundant, and I wish I'd said something else. So let's write a singular statement here to make sure we have sense, equals 18.4. Now the negative, as long as we have our picture and we can think about what's going on, we'll just ignore it here. Okay, let's write a statement. The ant, or the ant's velocity, and I'm going to use my shorthand, relative to the ground is, how fast is it going? .16 meters per second. Cool. At, and here's where I want you guys to, I keep erasing it and I keep using it. Okay, here was my picture, roughly, where that theta is my 18.6. I can't just say it goes at 18.6 degrees. That doesn't make sense in this problem. 18.6 degrees would be like this, and it should be going northeast based on our axes that we've made. Is that going northeast on the diagonal? So if that's 18.4, we need a better way to talk about that angle. How do we remedy it? Talk it out before me just telling you. I want a way to say that, no, I need this thing to go 18.4 degrees that direction. Yeah, exactly. So for the angle part, here's, I'm going to break the rule that I said I wasn't going to yesterday. I'm going to show you guys a couple different ways to do it, but they're hopefully simpler than saying here's 10 different approaches to a problem. This is just how we express the answer. This 18.4 degrees, I think it starts at west, right? We started left and went 18.4 degrees which direction? Okay, this bearing bugs the hell out of me. Just full disclosure. Like, I do not like it when it starts at west. Physics books do this. This physics book especially does this. Okay, this is not the only way to make sense of it. In my head, this isn't what I use. When I think about this problem, I think that this should be math. 161.6. This is what I would say. That's how I would word it. Huggins had a different suggestion. His suggestion, and help me out with the math here. Thank you so much. These three angles are the same. All three of them. Now, I prefer the middle one. I don't care which one you prefer. You can write it whichever one you like. Can anybody tell me how I get the middle one? So 90 plus 71, that's certainly how I get it, but I didn't know that 71. When we talk about angles, remind me, yesterday I made this big comment that this is just how we're going to treat them. Normally when we talk about angles, we start from where? East or the positive x, right? That 161 is just this angle in standard position. I've just written it the same way that we talked about the original angles, starting at the positive x and going that way. Any one of these would be fine. Cool. So, feel all right? Feel terrible? Cool. All right. Really quick brain break. We're going to do another one. Are we doing another one together, or are you guys going to try one independently at your desks? Can you guys do me a favor real quick? I'm going to ask that again. And I don't even care if it's like answering the question. Can everybody just make a loud noise of some sort? Like, it can just be a grunt. I'm fine with it. All right. Cool with that? Ooh, bringing it. I didn't hear grunts from you two. Okay, I like it. All right. So, for this, I I'm not gonna make you sit here and like watch and listen to a song for 3 minutes. That feels like it'd be super awkward. So now that I say that, maybe I should. 'Cause that's kind of my thing. I'm gonna play a song, and I want. Oh, I don't. Yes. I want you guys to try number. Ooh. I want you to try number 2 together as you're going through it. I want to get a couple things worked out. Read number 2 for me real quick. Once you guys actually start working, I'll play a tune up here. But I want you to read number 2, and I want to let's all agree on the subscripts that we're going to use to talk about it so we can compare easily. Okay, read through it, and we'll come together to like get our knowns and stuff in like 30 seconds. Okay, so just drawing the picture. I want to see your pictures just roughly, just to see what you're thinking here. Okay, so we have an angle there. Yeah, that's this one. An angle there. Okay, checking this out. Northwest. Can you guys point northwest? Like, are we just okay with still sticking with north, south, east, west is up, down, left, right? Okay, so here we go. A boat heads north, due north, west, not due north. Okay, on a river that flows due north. Okay, we are trying to find the velocity of the boat relative to the shore. So right off the bat, we have a river flowing due north. How would I draw a river flowing due north? Right, so I'm going to use this that's not very faint. I'm going to make it more faint. Okay, so here's my first axis, right? Okay, I have a river, which blue seems like a natural color for my river, heading due north. Sweet. Here it is. Okay, now when we write this, we already know the speed, and I saw that some people had it. That's 5 meters per second. I'm good with that. This is the velocity of what? The river, I think, right? And it's the velocity of the river or the water relative to what? The ground. They say the shore, but here's what I did when I did it. The river is made of water. I don't know if that's really it's an odd statement to make now that I say it. But I really care about how fast is the water in the river going relative to the ground. That's what we have. Now, R is a natural choice as well, but just to make sure we all agree, let's use this one for here. Okay, now beyond this, I'm going to do the same thing, and I'm going to draw like, hey, at the top of this vector, here's another coordinate system, just to make sure that we can make sense of it. So here it is. And what direction is this thing going? So we have a river flowing north. Love it. What's on the river? A boat. And which way is it heading? Northwest. Specifically, due northwest. What's northwest? Up and left. Okay, sorry to make you come steal those back. What color is my power boat? What's the color of power? Okay. You know that traditionally pink was the boys' color? Like little baby boys were pink?
And we were blues?
I don't think you guys were, maybe, I don't know. Pink is a derivative of red, which is power. Okay, so size-wise, should this next vector for my boat be bigger or smaller? Longer or shorter, I mean. Longer, significantly, and that's due northwest, I think. Now, the velocity that you've given me was 13, I'm fine with that. And that's the velocity of the what? The boat, and it's the velocity of the boat relative to the what? The river or the water in this case, right? Cool. Now, the reason that I would suggest, and I didn't check to see if you guys drew your coordinate stuff, the reason that I would suggest to do it is it's going to help us make sense of this. So the angles that we're going to deal with in red, this is how I'm going to write that angle theta. This is the theta, or the angle of the boat relative to the water, because I'm just going from that standard position, positive x-axis. That's why I draw it. This angle right here is the theta of the water relative to the ground. Now, if you don't want to draw it because it's going to like make it all too messy, what we're after in the end is the size and the direction of this yellow vector. And it looks like it works nicely, and it will, but when I look at these, here's my thought. I'm always going to do the thing relative to the ground first, because as I look at this and I think about taking this and this, what I see is that we're going to wind up with boat, ground on the outsides. That's, in my head, it's like they're just dividing out. You just remember a funny joke? Was it something I did? Okay.
Oh, but how do you know that the kid's gonna act like that?
So-
how do you know that the red one doesn't touch the bottom of the blue one?
It could. We're doing it this way because all year long we've done.
Get the tail.
Yep. You could do it the other way, and it just, I don't want to confound us right now, though. Okay, so as soon as we get here, my challenge for you is I want you guys, before you continue on with the problem, and I'm going to let you just like try this one, I want you guys to do the following. First, we'll turn up the ink. We need to identify the knowns. So we have them all drawn here, and some of them are easy. I'll try to stick to this color code. I'm going to do blue first because it feels like the ground is more important. You need the velocity of the water with respect to the ground. You need the angle theta of the water with respect to the ground. You need the velocity of the boat relative to the water. And you need the angle theta of the boat relative to the water. Cool. I'm going to give you guys a moment. Give me all these values. Once you think you have it, I'll give you the go-ahead as to whether or not I want you to move forward. Cool, 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 cool. If you're watching the video, pause it now. I'm not going to talk through this problem on the video, but you will see detailed work here when you unpause the video in 3, 2, 1. Okay, looking at this, it can be challenging. Now, if you looked at my notes, just full disclosure, I do this a different way. If you're curious, you can come take a look, but I'm not going to present it to everybody unless you want to see it. Okay, northwest is a specific direction. 90 degrees is what direction if you started east? North. Is there anything here that's traveling due north? What? The water. So right off the bat, I know that the water's angle is 90 degrees. Okay, I can see that. The next one seems like it might be a little hard, but it doesn't have to be. What's halfway between, so how many degrees are between north and west? So if you go halfway to get to northwest, it's 45, right? Okay, now I can't just say it's 45, and I'm not going to say it's just 45, because that whole angle doesn't start at the negative x-axis or at north. The actual angle is this much plus that 45. What's my angle? 135. Now, we do this to make sense so that when we plug stuff in, it's a little bit easier just to work through. We already had these written. There's my 13 meters per second. Gonna drive me crazy. And here is my lovely 5 meters per second. Cool. I want you guys, find me the components in the x direction of both the water with respect to the ground and the boat with respect to the water using that same formula that we did a moment ago, just with different letters. As you're working, we're going to listen to My Chemical Romance in Spanglish. As we look at this problem, without finishing it, because I don't know where my calculator is, if anybody has a calculator with Holloway written on the back, because I borrowed it to you, please let me know. Other things though, what do we get for the x direction? -9 something. It's positive? 9 point. I didn't hear it. 9 point what? 19. Okay, what about the y direction? 14.19. Okay, at this point, if you can get to here, you're golden. Now, these formulas that if you want to write them in that box, it's dependent on the problem. Your book uses object or motion relative to ground and object relative to motion is what they use. The letters that we use here change each time, right? It depends on what context we're in. But is the formula really any different? Relative plus relative, and we just use cosine and sine. Now, to make sense of what these numbers actually mean, it can be challenging, and this is a strange thing to think about because we're working with two different axes. It can feel unnatural to do this last part. The yellow part we just found, in the x direction, it goes -9.19, and in the y direction, it goes 14.19. This is the triangle that you've just found the components of in the end. From that, could you find the length of that hypotenuse? Then notice you also have the opposite side and the adjacent sides given right now, right? So my arctangent to get the angle. Tonight, is it mine? Oh, was it you?
No, it was
Oh, Angel. Tell her I was really mad about it. Cool. All right. I want you guys to verify. I'm going to give you the answer. Don't, like, you really do verify it. It'll in your best interest. 16.9, I think, meters per second at 33 degrees west of north. I probably rounded further. So let's look at that one. Everything went well except for that little part. I'm so happy with it. Tonight, I want you guys to do number 3 and try number 4. 16.9. Try number 3 and 4 tonight. 3, make sure it's done. Try it. I want an answer. 4, try it. It's awesome if you have an answer. But we done. Cool. Adios, studentes.